Good morning. Myself Dr. Jagdish, working as Assistant Professor 3 in the Department of Electronics and Communication Engineering, KPR Institute of Engineering and Technology. So now I am going to teach what are the applications of Laplace equation, especially in finding the capacitance and inductance. So you know the Laplace equation is del square V equal to 0. So based on this equation, now I'll explain you how to derive the capacitance of a parallel plate capacitor. So for this, let us take a parallel plate capacitor where we have two plates which is separated by a dielectric medium. Let us assume this parallel plate is along y-axis in a Cartesian coordinate system, and the distance between the two plates Vd, and this capacitor is having a voltage of V0. So this is our assumption. So as we know, this del square V equal to 0. So now, since it is Cartesian coordinate system, this can be written as dou square V by dou x square plus dou square V by dou y square plus dou square V by dou z square is equal to 0. Since your parallel plate is along y-axis, the x component and z component will be 0. So my equation reduces to dou square V by dou y square is equal to 0. So now, it is dou square V by dou y square is equal to 0. Now I am going to integrate on both sides. So if I integrate, this equation becomes dou v by dou y is equal to a. A is nothing but your integrating constant. Again, if I integrate, my equation will be v is equal to ay plus b. My a and b are integrating constants. Now let us apply the boundary conditions to find the integrating constants a and b. So my boundary condition will be, I have two boundary conditions. One is y is equal to 0, b is equal to 0. Second, y is equal to d, because the distance between your two plates, and my voltage will be V0. Now we apply the boundary condition in equation 1. So if I apply my first boundary condition in equation 1, my equation becomes 0, d is equal to 0. Now if I apply my second boundary condition in equation 1, so my equation will be V0 is equal to a into d plus b. Since my d is 0, this equation becomes V0 is equal to a into d. So my V0 is a into d. Now you know the relationship between electric field intensity and electric potential, which is E is equal to minus del V. So this gradient, this can be replaced as dou V by dou Y. So if I substitute my equation and differentiate with respect to Y, my V will be minus V0 by D. So this is my E. So E will be minus V0 by D. So you know the relationship between flux density and field intensity. D is equal to epsilon into E. So my D vector will be minus epsilon into V naught by D. So far we have computed what is my flux density of my parallel plate capacitor. Then, so you know the formula to find capacitance. Capacitance is nothing but C is equal to Q by V. The amount of charge stored in the capacitance with respect to your voltage current. Now, so we have computed V. Now you need to find what is my Q. So what is my relationship is Q is equal to rho S into A. Q is equal to rho S into A. Where rho S is surface charge density, rho S is surface charge density, and A is your area, A is area. Now based on this, you can say, so my surface charge density rho S is nothing but my magnitude of my flux density T delta. So my rho S will be epsilon V naught by D. So if I take magnitude, so it is epsilon V naught by D. And your A is nothing but your area of the capacitor. So my area of capacitor, the total area of this capacitor is A. That is K. The area of capacitor is A itself. So now what is my Q is? Q is epsilon V naught A by B. So this is my Q, that is my charge stored in your capacitor. Q is equal to epsilon V naught A divided by B. Now, if I substitute in my capacitance equation, C is equal to Q by V. So this becomes epsilon V naught A divided by D divided by B. So here my V is nothing but V naught. So let the total voltage of your capacitor is V naught. So it becomes C is equal to epsilon V naught A by D divided by V naught. So V naught will get cancelled. So my capacitance C will be epsilon into A by D. Epsilon into A by D. So you know epsilon, the relative permittivity is epsilon naught into epsilon naught. So if I substitute, my capacitance will be epsilon naught A by D. So my capacitance of a parallel plate capacitor will be epsilon R into A by D, where epsilon naught is your permittivity of your free space and epsilon R is your relative permittivity, A is your area of the capacitor and D is the distance between your two parallel plates. So from this equation what we infer is my capacitance does not depend on your voltage. My capacitance is independent of the voltage level what you are going to supply to your capacitor. So it purely depends on your area of your capacitor, distance between your two parallel plates and your permittivity of your material what you are going to use. So this is a simple application where we can use your Laplace equation and Poisson equation to derive a capacitance of a parallel plate capacitor. So this we have derived with respect to your Cartesian coordinate system. If you want, you can derive with respect to cylindrical coordinate system and spherical coordinate system. So you can take r, theta and phi or r, phi and z to derive your capacitance of your parallel plate capacitor. So based on this Laplace equation, we have derived your parallel plate capacitor. Likewise, you can also derive for spherical capacitor and a spherical capacitor. The another one is coaxial capacitor. So you can also derive the capacitance of spherical and coaxial using your Laplace equation. And also you can also derive for your inductance. You use your Laplace equation and Poisson equation to derive inductance of a solenoid and inductance of a toroid. So these are some of the applications where you can use your Laplace equation to find the unknown capacitance and inductance of any material. Thank you.